Hello, today we'll talk about the concept of wettability, lecture 12. So to first start talking about the concept, first let's study different properties, and the first property that we want to study, or definition, is interfacial tension, as we can see over here. So the easiest way to define interfacial tension, and interfacial tension has the symbol of sigma, that it equals to force per unit length, and that would have unit of Newton per meter, or we can have it as dynes per centimeter. And 1 dynes equals 10 to the power negative 5 Newton. So to study interfacial tension, we can look at the system that we see over here, and we have 2 points of interest, point A and point B. So for point A, we can see that the water molecule is actually saturated and it's fully occupied, so everything's fine. However, in point B, since the water molecule is touching the surface, there's actually imbalance in the molecules. And once this imbalance actually happens, it causes a tension in the surface, or a surface tension. So when this tension is formed, it's like a strong force happening on the surface. And maybe you guys saw this before in different videos or photos, is that sometimes we can actually place like a denser object on top of the water and it will not sink. And that's due to the interfacial tension. So to elaborate more on surface tension or interfacial tension, because now you've heard that I use two different terms, interfacial tension and surface tension, is the following. So interfacial tension and I also have surface tension is that both they have the symbol sigma. However, the main difference is that for interfacial tension, it's actually between two different fluids. However, for surface tension, when we use the term surface tension, it's usually between solid and fluid. And again, in terms of the units, they would all have the same unit system, and that will be Newton per meter if we're using SI units. To jump in and to discuss more of the applications of interfacial tension, we can refer to this image over here. And what we see on the left-hand side, we have oil and water with clear interface. However, if we look on the right-hand side, it's hardly to see a visual clear interface. So here, when we have a clear interface, we can clearly see the interfacial tension, like the sigma, and that here it means that the sigma is actually high to cause this clear interface. While when we have the lower interfacial tension, then it's hard to visualize a clear interface, so it means that sigma over here is low. And there's one term that we can use that we'll use frequently in the course is the concept of miscibility, if whether the fluids are miscible or if it's immiscible. Mainly we'll focus on immiscible. So when we say the fluids are immiscible, it means that they do not mix. All right, and now what we will do, we'll gather the stuff that we learned and take it to the next concept. So now let's talk about wettability. So wettability, in terms of the concept, is that it is a phenomenon that we have seen in our daily lives, in every single day, almost. So the concept revolves around the materials that we use and whether it's like certain fluid in comparison to other fluids. For example, if you have a tissue paper or if you have umbrella fabric or the rain cloth that we use, is that the umbrella fabric does not like the water, so it repels the water, while tissue papers actually like the water, so it absorbs the water. And that's the definition or the concept of wettability. So if I want to define the concept in words, then wettability is the preference. Let me just write it down. So wettability is the preference of one fluid to be in contact with a surface in the presence of another immiscible fluid. And to study the wettability in more details, we'll have to look at the concept of contact angle, and that will be the second point. So let's imagine that we have the system, and in the system we have water, we have gas, and we have the solid, which is our surface that the droplet over here is spreading on. And beforehand, let me define two things. That will be cohesive forces and adhesive forces. So cohesive forces is forces between similar molecules, and adhesive forces is actually the force between different molecules, meaning that if the water molecules would rather to stay together, then the cohesive forces will be stronger than the adhesive forces. While if the liquid wants to spread on the surface, then it means that the adhesive forces are stronger, and that will make the droplet spread on the surface. So cohesive forces between similar molecules, and adhesion force or adhesive force is actually the forces between different molecules. Okay, so now if we want to analyze the droplet that we have, let's see it over here and zoom in, we will study the object from point A, and I'll refer this one to point A. So let me draw down the axes. So I have here my positive y-axis, negative y, and then I will have my positive x and negative x. So now to study what's actually happening over here. So at point A, we actually have the water trying to spread. And at point A, the water is trying to spread that way, trying to spread from both sides, so this way and that way, but at point A, it's going that way. And that, in terms of the sigma, it will be the surface tension between the water and solid. And then on the opposite side, we also have the surface tension between the surface and air or gas that's trying to also maybe trying to fight and trying to get spread on the surface. So what we have over here is we also have a sigma of gas solid. So it's trying to move that way and the water trying to spread that way. Okay? And then the last thing, we also have a sigma over here, and that sigma is actually between, let me change the color, sigma between gas and water. So if I want to study the total forces or the total sigma in the x-axis, so sigma of sigma x, then what we will do based on the axes at point A that we develop, and that will be at point A, then we have sigma gas solid minus sigma water solid, since it's going toward the negative axis. And then if we want to study, and that's only at the x, then this is theta. And by the way, theta is contact angle. So this over here, then in this case, then we'll have plus sigma gas water cosine theta. And since the system is actually at rest, then the sigma will be 0. And then we can adjust the equation to redistribute and reorder to find theta, or the contact angle. So let me proceed here. So in this case, I'll just move these two to the other side. Then that will be sigma water solid minus sigma gas solid equals sigma gas water cosine theta. And before we proceed, this term over here, we refer to it as adhesion tension. And adhesion tension, the concept, is actually responsible whether the fluids are going to spread or they're going to shrink. So the value will indicate if the system is actually spreading on a surface or if it's shrinking, if it's like the surface or if it does not like the surface. So the final step to find theta, which is the contact angle, it equals to sigma water solid minus sigma gas solid divided by sigma gas water. And that's our theta from this system. Now, to take this theta and study it more, we'll go to identify or classify the different wettability states. So to understand the different wettability states, we can subdivide them into 4 different types. And to start with, which is the one on our left-hand side, is water wet. And how do we know it's water wet? Because you can clearly see that the water droplet is actually spreading on the surface. And what I mean by water droplet is that this is water and surrounded by oil. And beforehand, when I go back to this system over here, just to quickly say, is that this can be applicable to all different systems and fluid pairs. So it can be for oil water, it can be for oil gas, or for water gas as we displayed. So it's not limited to water and gas only. So to go back here, so you can see that the water is actually spreading on the surface, and that will make the contact angle to be less than 90 degrees. So to define water wet system is that we can say that the system is water wet because the surface likes the water, so it will spread, and the contact angle, which is theta, will be less than 90 degrees. So that's the first concept. And one of the things that you can see is the tissue paper or the towels that we use should be all water wet because they're absorbing water because they like the water. Now let's go to jump into the next one, which is, and this one has 2 different like names or definition, 2 different names. The first one is neutral wet, or intermediate wet. And in this case, the surface has equal affinity towards oil and water. So it has an equal preference to be in contact with oil and water. So it's not like more preference over the other, so it has equal preference. So it has neutral or intermediate wet, and the theta should be around 90 degrees. So the surface has equal affinity towards oil and water, and theta should be around 90 degrees. And then the third case is actually quite the opposite to the first case, and that's oil wet. So for oil wet system, in this case, the surface likes the oil and hates the water. So if you put a droplet of water on an oil wet surface, it will be like form like the bubble, and you can easily displace that bubble out because the surface doesn't want to be in contact with the water. It prefers to be in contact with the oil. So this is for the oil system, that the surface likes the oil and hates the water, and theta, which is contact angle, will be greater than 90 degrees. And when we say theta is greater than 90 degrees, we're referring to the water droplet on the surface. So if we're dropping an oil in top of oil wet surface, then theta will be less than 90 degrees because it's like a surface and it will spread. But if you place water on top of oil wet surface, then most probably it will try to have a high contact angle because it can be easily displaced out of the surface. And then the final state that we have, and that can be also referred to it in two different names. The two different names that we have are mixed wet or fractional wet. And in this system, for the mixed wet or the fractional wet, is that the system actually has affinity towards. So it can be, so the region that actually prefers to be in contact with water wet and another region that prefers to be in contact with oil wet. So we can have two systems in one. So here, if you look in the system, then this system here, this region is water wet, while this region is actually oil wet. So to define it is that part of the surface is water wet and the other part is oil wet. Okay, and most people actually confuse mixed wet with neutral wet. So neutral wet is the system has equal affinity to both, while in mixed wet is that part of the system likes the water and part of it likes the oil. So now let's move on to the next section. And in this section, we'll introduce two new definitions, imbibition and drainage. So to talk about them, and by the way, let me go back to discuss one more point, is that in a water-wet system, water is the wetting phase, while oil is the non-wetting phase. So the wetting phase is actually what the system likes. So in an oil-wet system, oil is the wetting phase, and water is the non-wetting phase. So to go back to the definition, imbibition imbibition is the increase of the wetting phase and drainage is the decrease of the wetting phase. And we will discuss more, and we'll discuss both of them in more details once we talk about capillary pressure. But I just want to mention that this definition can also be thought from the opposite point of view, meaning that imbibition can also be the decrease of the non-wetting phase, and for the drainage, it can be defined as the increase of the non-wetting phase. Okay, and we'll come to this concept again once we talk about capillary pressure. So now let's move on the importance of wettability. And in this system, we actually have three different units or three different systems on the left-hand side, in the middle, and in the right-hand side. So the first thing for us is to identify the wettability. We can easily identify the wettability as the following. So on the left-hand side, I can say that the system is oil wet. And the reason that it is oil wet is that because oil is surrounding the grains and it seems that the grains actually love to or prefer to be in contact with the oil rather than water. And as you can see here, all the grains are surrounded by oil. So that indicates that the system is oil wet. On the one in the middle, I can say that the system is water wet because water is actually surrounding all the grains. So the surface actually prefers to be in contact with the water rather than the oil. And in the last one over here is that the system is mixed wet because there are actually regions in the system that are water wet and there are regions that are oil wet. The lower part is oil wet while the upper one is water wet. So it exhibits both fractions, water wet and oil wet. So now let us discuss the importance of wettability. And based on this, I can tell you two definitions. The two importance. The number one is that wettability controls fluid distribution in the pores. And the second one is that wettability controls the oil and water flow rates. And we'll discuss this part more when we talk about relative permeability for the second part. So as we can see, the fluid distribution is actually very different across all of them, and that's due to the wettability and what the surface actually prefer to be in contact with. So with that being said, let's discuss the different methods to define or to measure wettability. And for that, we can actually classify them into different types. So for wettability, there are direct and indirect methods. So for the direct methods, there are two methods that we can use, and they are contact angle measurement, and there is the Ammot index. However, for the indirect, we have three main methods, and they are capillary pressure, mainly the imbibition pressure, and then we have relative permeability, and then finally we have residual saturation. Okay, saturation. And we'll discuss all of these, but at different times, but now we'll focus on the direct methods. So the first method, which is the contact angle, it's actually a very straightforward and simple method. Imagine that you have your rock surface that you want to study or a surface that you want to study, and what you will do is that you will place the system or the surface that you want, and then you will drop the droplet that you want to study, water or oil, on the surface, or we can use water and oil depending on the cell and system that you use. And then using a high definition camera, what you can do is that you can zoom in and you can capture a clear picture of that interface or that system. And then using software, you can measure the contact angle using the software and identify the value of the contact angle, and hence you can find the wettability. And I can also say that there are actually different cells that you can use, and these cells can actually, you can measure or do the experiment at higher pressure and temperature using different fluid bearers, using all different systems that you want on the surface that you want to do. So it is a very straightforward. The second method, which is the Ammot index, it's actually a qualitative test to find the wettability. So what actually happens is the following. So imagine that we have a rock sample, Okay, and this rock sample initially has water and oil. So we'll refer to this as our initial phase or initial saturation. So that will be at point A, and the water saturation at that point will be SWA. And we can find the water saturation using either the volumes that we have measured or using material balance. So after that, we take this core sample and place it inside the ammote cell, which is the one that we see over here. So the ammote cell, what happens is once we place the core sample inside, and assuming that the core sample is water wet, what will happen is that the rock will absorb water. And once it actually absorbs water, what will happen is that it will expel the oil out. Okay, and since oil is less dense than water, it will migrate upwards, and then we can either record the volume of oil that we have over here, or we can, after we finish, we can extract the core sample from the cell and weigh it, and by using material balance, we can find the fluid saturation. So here, what's actually happening is that the rock is spontaneously imbibing water. And we said again, imbibition is the increase of the wetting phase. If the rock is water wet and the water phase is increasing, then the process is imbibition. So we refer to this process as spontaneous imbibition. And when we say spontaneous imbibition, it means the natural increase in the saturation. So it's natural, we're not applying any force, we're just placing the core inside and surrounding it with water, and that will be the saturation. So after this process actually is over, so we'll refer to this as stage B, and the water saturation after we finish will be SWB. And after we finish from this stage, we extract the core sample and we place it inside a core holder, as we see over here. And now what we do is that we're forcing the water in. So now we're injecting the water using the pump and we're forcing it inside. So that will be point C, and that will be forced injection because we are forcing the water in. And after we finish, the saturation at that point, we'll refer to it as SWC. So at this stage will be SWC. And now let me just zoom out and talk about some concept, and then we'll jump back again. So for the ammote index, it has the symbol of IA, and ammote index is divided into, or subdivided into two parts, and they are the water ammote index, or the ammote water index, which is IW, and we have the ammote oil index, which is IO. So now let's discuss IW since we already finished that part of IW. So IW, which is the ammote water index, equals the following. Equals SW at point B minus SW at point A divided by SW at point C minus SW at point A. So what really happens is the following. So on the upper part, we're actually comparing the spontaneous imbibition to the initial saturation, and in the lower part, we're actually comparing the forced injection to the initial saturation, and that's the ammote water index. And then to complete the ammote index, we need to find the ammote oil index. And to start the ammote oil index, so we start from where we left with, and that will be SW at point C. But for the ammote index, for the ammote oil index, we need to analyze oil saturation instead of water saturation. So what will happen is that we need to start from this point. So instead of having SWC, we'll have SOC, and SOC equals 1 minus SWC, since we're dealing with two phases only, which are like oil and water. Then, in a similar fashion, we'll take the core sample that we just finished with from point C, and we place it inside Amut cell, the same Amut cell, but instead of surrounding the core sample with water, we'll surround it with oil, as you can see over here. And now what we will do, we will invert the Amut cell, and that's because of the density difference, that now if the rock likes the oil, it will absorb the oil, and it will expel the water out. And if we want the water to be recorded, we have to invert the cell so we can record the volume of water left. Or after we finish, we can just extract the core sample from the cell and weigh the core sample to use material balance to find the core. So that will be here at SW at point D. So this is point D. And the final stage that we will encounter is that we will extract the core sample from point D and place it inside the core holder. And what will happen is that now we will inject the oil inside. So we're forcing the oil in to displace the water. So what will happen after we finish, that will be our point E, and that's again forced injection. So we're just repeating the same thing that we did for the water index for the oil index. So that will be forced oil injection, and the oil saturation will be SO at point E. So now to complete the study, we have now IO, which is the oil Amut oil index, and that will be SO at point D minus SO at point C divided by SO at point E minus SO at point C. So what we were doing, again, we are also comparing the two stages, which will be the first one, we're comparing the spontaneous phase to the initial phase, and that will be divided by the forced phase minus the initial phase. And finally, the Amut water or the Amut index equals the Amut water index minus the Amut oil index. And to identify the wettability, so for water wet, IA, which is the Amut index, should be between 1 to 0.3. So any value between that will actually indicate that the system is water wet. And then we have neutral wet, and that means that IA should be between 0.3 to negative 0.3. And finally, we have oil wet, and that should indicate that IA should be between negative 0.3 up to negative 1. So any value of Amut index within this region should be able to indicate the type of wettability that we're dealing with. And again, this is a qualitative test to help us identify the wettability of the core sample. So now let's do a problem. And in this problem, it's mainly about the Amut index. So to read the problem, there's a core sample initially contained SW equals 25%. So that's the initial water saturation. The core was placed in an Amut cell surrounded by water for a few days. So that's the spontaneous imbibition phase. After extracting the core, it was found that the water saturation increased to 68%. So let me just highlight every part and discuss. So this is my initial saturation. So that will be my SWA. And then the second phase that we have is this one, which is SWB. And then when the core sample was placed in the core holder and water was injected, so that's the forced injection, at a high flow rate, the water saturation in the core after water injection was found to be 72%. And then when the core sample was placed in an Amut cell surrounded by oil, very little oil imbibition occurred and the water saturation decreased to 71%. When the core sample was placed in the core holder and oil was injected to displace water, the water saturation reduced to 32%. Based on the data collected, what is the wettability of the core sample? So now let's just analyze what we have. So we need to do two things. We need to find the water index, oil index, and then eventually we'll have to find the ammonia index. So based on these parameters that we have, so we have here SW at point B, and this one will be SW at point C. And then here we have this one, and these are all water saturations that we need to convert to oil saturation. So this will be SO or SW at point D, and this one will be SW at point E. So what we will do, so the first thing is IW, which is the amount water index. And by the way, what we will do is that we will revisit the concept of Ammott index once we go to capillary pressure and imbibition curves, that we will hopefully visualize the concept using different saturations, so that will be easier to comprehend the topic. So for IW, we have SW at point B minus SW at point A divided by SW at point C minus SW at point A. So what will happen is the following based on the saturations. So SW at point B is 0.68 minus 0.25 divided by 0.72 minus 0.25. And that should equal to 0.915. And that's our first value. Now for the second part, we need to find IO, which is the Ammott oil index, and that will be SO at point D minus SO at point C divided by SO at point E minus SO at point C. So before we proceed, we have all water saturations that we need to convert to oil saturations. So in order to do that, we have the first point, SO at point C equals 1 minus SW at point C, which equals to 1 minus 0.72, which equals 0.28. And then the second point that we have, which is SO at point D, equals 1 minus SW at point D, and that equals to 1 minus 0.71, which equals to 0.29. And then the final one is SO at point E, which equals to 1 minus SW at point E, and that equals to 1 minus 0.32, and that equals to 0.68. Now we can plug in all the numbers, and that will be, here we have 0.29 minus 0.28 divided by 0.68 minus 0.28. And the answer here will be 0.025. So now we have both the water index and the oil index. So the final step for us is to find the wettability index, the Ammott index. IA equals to IW minus IO, and then that will be 0.915 minus 0.025, and the answer will be 0.890. And if we look at the categories for different stage, then we can clearly say that the system actually falls within the water wet stage. With that being said, we finished the lecture. Thank you very much for listening.